Good day, everyone. Thanks so much for joining. I know we've got a couple of minutes here while we have different participants get into the room. I'm going to allow a couple of minutes here before I start. I hope everyone's doing well today that is already in the room. Thanks so much for being here. My name is Bruce Thacker, and give me just a little over a minute and I'll be right back to start the presentation. Good day, everyone. Thanks so much for being here. My name is Bruce Thacker. I'm with CSI Amatech. Really appreciate the opportunity presenting at the Kister Distillation Symposium this year. Thanks so much for your time. Want to get started here right on time. Thanks again for joining, and we'll start with a presentation on heating system design based on the upset condition. So just change over to the slides here. And here we go. So for our abstract today, continuous distillation throughput can be limited by operational issues with product solidification or plugging in interconnecting and downstream piping and equipment. These events, while rare, have historically incurred high cost and lengthy timeframes to rectify, reducing unit profitability. This presentation will examine specific operational upsets and the solutions plants implemented to eliminate or shorten future downtime occurrences due to plugging in tower bottoms and downstream lines. We'll also discuss general heating system design objectives that consider upset conditions to prevent issues and guard against and/or allow for quicker, more cost-effective recovery after events. So for the agenda, we're going to do a brief distillation unit overview. We're going to talk about those thermal objectives for the process lines and the heating systems for both steady state and upset conditions. We're going to look at the heating system performance comparison relative to those objectives, look at a few operational challenges and the solutions that were employed to overcome them, and look at best practices to prevent or allow quicker recovery from future occurrences. So background, distillation units, like most refinery or chemical plant units, maximize profitability through continuous operation. It's the first step in the refinery process, and it's a critical gate to overall efficiency. And the general nature of the distillation process is to separate the lighter components from the heavier ones, of which the heavier ones' bottoms are drawn off of the tower. So piping and equipment that's moving between these towers and downstream of them typically do not need robust heating systems. In fact, most times no heat input at all to keep the process temperatures at the right levels. However, these heavy products can present issues when their temperatures are allowed to drop. Therefore, ensuring they stay hot is a priority. So issues are rare, considering 99% of the time plugging and other temperature-related processes are typically seen as anomalies because of a high efficiency run rate. But when they do occur, there's really large cost implications that the refineries can incur, as the most recent freeze situation in the Gulf highlighted. So we're going to provide a closer look into these anomalies, how the heating technology selection, when properly applied, can yield quicker recovery from these issues and reduced or eliminated downtime. So first of all, we need to look at what are the thermal objectives for this piping system. What's important to the plant relative to that liquid process that's moving in between these towers and downstream of this towers? Well, number one, maintaining the temperature of that process above its melt point is a great idea in a flowing condition and in a no flow condition. Also, if there is an upset and that process line goes to ambient, it would be really good if that heating system could take it from ambient to its flowing condition on its own without the need or the input from any other parts of the plant or any other outside. So when we look at those three objectives, we want to take a look at, well, what technologies are available that can meet those, and then let's do a deeper dive into pros and cons of those. So unlike a few decades ago, there's a lot of technology that's available today that can really help us in those three objectives. There's the historical tube tracing that's out there. Most of these units have been designed for this technology from the beginning. We're going to look at an enhanced tube tracing system, and we're going to look at an engineered tracing system. As you can imagine, as you go from left to right across the screen with these different systems, the heat demand goes up in terms of the capability of those product lines. And so we'll study a little bit closer as to why those different product lines may be of use in selecting the heating systems for these particular lines. So when we look at tube tracing, most everyone has seen tube tracing in these plants. It's the most common tracing for refineries and chemical plants in the world. Essentially, you can see a couple of examples here. It's convective heating. You have a circle against a circle if you look at a cross section of the pipe. So if that circle is touching the other circle, it's a minimal point contact. So what this system is doing is it's heating the air that's between the insulation and the pipe that's around that tube tracing. And so therefore it's convective heating. When you start graduating into enhanced heating systems, enhanced tube tracing is essentially taking that bare tracer and putting a cap over the top of it, which increases its heat input. That cap, when filled, or that void when filled with heat transfer compound or mastic, then provides a conductive heat path into that piping. So you can see a few examples of one of the products that's out there, an enhanced tracing system called Trace Boost. That turns that bare tube tracer into conductive heating. So now we can drive a lot more heat into that system than we could with just that bare tracer. And then we can graduate to an enhanced tracing system. So here's an example of an enhanced tracing system, an even more robust system that affords even more heat input into the process. Again, with a heat transfer compound or mastic between the heating system and the pipe itself. Here's some examples of what a system like that may look like for heating piping, for heating valves and equipment, tanks, vessels. Here's an installation drawing for one of those types of systems. A much more robust system that affords a lot more heat input into the process. And again, a conductive heating system. So if we've talked about a flowing condition, we're looking at process movement between these towers, downstream of these towers, which in normal operation with a flowing condition does not need heat. So you can see in this graphic, there's a lot more heat input than lost to ambient because of those factors, because it's flowing, because it's hot when it comes in, because the piping's insulated. And so a flowing condition does not need heat in the 99.9% of the times, and certainly around these units. So what does that mean in actuality? Well, simply stated, any heating system that's put on these lines to heat them will work as long as the process is flowing. In fact, if you could ensure a continuous flow without a risk of an upset or a stoppage, these lines could be insulated and left unheated permanently. No heat needed. So if that's the case, well, how far could this process travel without any heat whatsoever? So here's a chart that demonstrates exactly that. This is Bottom's product, or vac resid, that's flowing from a 750 Fahrenheit temperature. We want to keep it above 300, roughly 300 Fahrenheit. And so in this example, with no heat in an insulated line, that product will travel 25 miles before it needs 1 BTU of heat. So if that's the case, when do we need heat? Well, heating becomes critical when the normal operation is compromised due to an upset. Anytime the process line stops. When may a process line stops? Well, if a pump goes down, if a piece of rotating equipment has a failure, if the plant loses steam, all of these issues that stop the process flow then demand heat input from the heating system. And then, and really only then, is the heating system going to be tested. And if the heating system can't perform at that time and under that upset, then there's going to be a major problem the refinery is going to have to deal with. So when we look at the no-flow condition, it's more difficult to achieve because we actually have to put some BTUs into the process now. The system has to be modeled for those BTUs to make sure the temperatures stay at their right levels. And the thermal capability of the technology also has to be considered because we need to make sure that whatever we're recommending and putting on those process lines can achieve that thermal objective. So if it's an inadequate system, then the heat losses are going to overcome the heat inputs. If it's a properly sized system, then the heat losses are not going to be greater than the heat input, and so therefore that system can maintain that process condition. Here's what that chart looks like when you look at the heat loss chart with each of those technologies. There's our melt point line. There's our design conditions that this chart is based upon. We're going to look at time to solidification, which is roughly 300 Fahrenheit by technology for bare tubing, which is represented on the chart by the purple line. We're going to look at the enhanced tracing, which is represented by the orange line, and the engineered tracing by the burgundy line that's on there. And when you look at the time to solidification for those technologies, tube tracing, 15 hours. So as long as the upset or whatever the stoppage is for that line is controlled and allowing the process to continue within 15 hours, bare tracing will work. If it does not, or if it takes longer, if 15 hours is not enough time to address the issue, then that process will solidify and that bare tube tracing will become a problem. When you look at enhanced tube tracing, conversely, and its performance, the heat loss is not enough to keep to force the product to plug, and so therefore that technology will maintain indefinitely the process temperature above the melt point. Likewise, the engineered tracing in this case, same story. You can see from the graph there that both of those technologies would be an adequate solution here if the plant experienced a shutdown longer than 15 hours. So another thing to keep in mind, if the tracing cannot maintain the temperature during no flow, it also cannot melt out, which brings us to our next thermal objective, melt out. So melt out is the most difficult to do because you have to drive the most amount of BTUs into the process to get it from ambient back to that flowing temperature. It requires a lot of times a much more robust heating system to accomplish, especially if there's a time frame that the plant is looking for that they want to achieve this melt out. You can see here, you have to make sure that the heating system is properly designed to drive enough heat in to meet that melt out time frame. So here's that same chart. When you look at melt out, there's our melt point, there's our process conditions. We want to melt out, understand the melt out time frame from ambient to that 300 Fahrenheit degree temperature for bare tube tracing, for enhanced tube tracing, and for engineered tube tracing. And so the tube tracing, as you probably can surmise, it's not possible. In fact, from the chart, you can see that the tube tracing would never make it above 200 degrees Fahrenheit in that situation. So if you go stagnant with this type of a system with bare tube tracing, then there's going to be remediation activities required to get back up and running. However, the enhanced tube tracing can melt out that process within 2.7 hours under these conditions. The engineered tracing can melt it out in 1.2 hours under these process conditions. So very valuable for a plant that has typical shutdowns, often shutdowns, to look at potential enhancements to the heating systems to prevent issues with plugging product. And so when you look at the plugging product, we're looking at the meltout conditions. So if you have a plugged line, what are the historical remediation methods that plants went through? Well, usually it's an emergency call to electric heat blanket vendor. They have to come in and melt out the lines, which requires a lot of activity. Insulation has to be removed and reinstalled. The heating company has to come on site, hook up the heating blankets for a period of time. There's usually a rather large daily rate to have this process take place, and you have a lost production time while it's taking place. Another way that plants circumvent this is when they know they're going to have an upset, or a turnaround, then there's a line flushing that can be employed. And this is cutting the process lines with finished products to circumvent the plugging. So, of course, you can probably imagine a lot of resources need to be dedicated in order to implement the cutting process. The stored system, the flush product has to be ran to tanks, has to be ran through rotating equipment, has to be reprocessed again, which leads to double processing, lost production time, and a short period of time for operations to get the lines flushed when perhaps their time is better spent on other events related to the shutdown or the turnaround. Finally, mechanical removal, which isn't as prevalent anymore, but can be used to remove those plugs, which is hydroblasting or steam lancing. But if they are used, this presents a safety issue for the plants. So looking at some specific applications where these issues may happen, just throwing a few on the screen there for you, but any of these heavier product lines, the bottoms lines between the towers, the bottoms lines as they go away from the tower and into the other units, these heavier hydrocarbons tend to really cause problems because they're a more viscous process line anyway. So here's a couple of examples of some of the befores and afters for these lines, especially around distribution stations and what that, in this case, an engineered system may look like. So when we look at a couple of examples of different clients that have went through these issues, this is a bottoms or a vac resid meltout application where we had large bore piping, tube tracing originally on the line. The tube tracing, as demonstrated in the presentation, could not melt out after the upset. So this particular client wanted to change the technology to something that could melt out within a 24-hour time period. And so the original technology of tube tracing did not work. The revised technology, in this case of an enhanced tracing, could achieve that melt out within that time frame, and therefore it was selected. For client B, this was a no-flow and melt-out situation where coker feed pump suction and discharge lines had issues where the pumps were the problem. The pumps would go down, the process would sit in the line. When it sat in the line for enough time, it plugged, and then the tube tracing that was heating the line could not melt it out. So their remediation is they had to call the heating company, the heating vendor, to come out. Over the course of a year, the remediation costs ran in excess of $2 million for the plant. What they decided to do was change to engineered tracing so that they could have the minimum downtime when those pumps did fail, which achieved both thermal objectives. And it paid for itself within between 1 and 2 months of being in operation. Final example of some bottoms and coker line flushing as part of the shutdown. So this particular refinery had tube tracing on their lines. They knew that they would cause a problem during shutdown, so they enacted a procedure to flush the lines ahead of the turnaround, and they essentially got tired of doing that. They wanted to come up with a tracing system where they could dismantle the flushing and eliminate that as a source of added cost and as well as added time. And they changed to engineered tracing. One unique thing about this application is the plant had a plant-wide power outage a couple of years later, and when they started the system back up, this particular line was the first line that thawed out after the line came back up to power. So again, the original technology of tube tracing, and in this case, the selected technology was the engineered tracing system. So how do we prevent future issues? Well, liquid processes have historically been designed for flowing conditions. Our thoughts on that is to support a paradigm shift toward no flow and melt out as maybe more appropriate design conditions for selecting the heating systems. And the best way to minimize cost, reduce rundown, maximize throughput is to include P&ID notation that addresses these conditions. And an example of that for, say, a bottoms product would be right here on the screen: heating system to maintain minimum process temperature of 325 at all times, melt out from ambient to that temperature within 12 hours after loss of utilities. Heating system vendor to provide calculations showing compliance. So what this does is it satisfies all three thermal objectives and provides governance to ensure the heating system vendor confirms compliance. So in conclusion, the best way to reduce or eliminate downtime is to design the heating system for the three thermal objectives. We know already that the flowing condition is not really a design condition because flowing processes don't need heat. They need heat when processes are at no flow and/or the plant is trying to melt out the product from ambient to that particular thermal maintenance temperature. So CSI Amatec, just as a brief overview, is a technology neutral engineered solutions provider. We focus on helping solve our clients' most challenging issues and specialize in liquid and vapor heating systems and specialty products that address plugging and corrosion in refineries and plants. We welcome an opportunity to assist with finding solutions to problems affecting safety, maintenance, and throughput. And I thank you very much for your time today. I'm going to be available for questions should any arise, and I hope everyone has a very safe day. Thank you so much for your attention.